Okay, for those of you who are watching, I'm doing the recording in QuickTime instead of iMovie. I'm not sure if that'll make any difference at all, but it might be something that's more convenient anyway. So if there's any noticeable drop or improvement in quality of this video, that's done in a different way, by all means, let me know. Thank you. Okay, so last time I started talking about the method of characteristics for first order PDE. Now, between Wednesday and today, I went back over those notes because sometimes different books describe things differently, different definitions, which is a different notation. So if you've downloaded the notes for Wednesday, that's lecture 3, I suggest downloading them again. So I've made some changes to bring everything more in line with the textbook, and also today's notes. Now, if you're a little sketchy on the method of characteristics after Wednesday, that's perfectly okay, because students always like to have more examples, and today is nothing but examples of method of characteristics. The homework 2 problems are up. Well, so you got them already. So for chapter 2, what?
I know. I think
that is the list you got, right? Okay, yeah. So there are just 5 problems, and chapter 2 is a longer chapter. We're only just starting it. So we'll get. So the homework is not due for another 3 weeks. But some of that stuff's not till the end of a chapter. So even after today, you should be able to do the first 3 problems, and then the other 2 will come later. Okay. All right. So, yes, so definitely want to. Okay. All right. Now. This is 2.4. And what you're going to see is, through these examples, I have like, how many? Okay, 5 of them. Hopefully I get through all 5 of them today. We're going to be following the same procedure, and there may be slight differences depending on whether the PDE is linear or nonlinear. But hopefully with enough repetition you can see how the steps are supposed to go. Okay. So, first example. So our initial value problem, IVP, which is also known as a Cauchy problem. So whenever you have only an initial condition, you do not have any boundary conditions, because your domain is just infinite in all directions. Then it's just a Cauchy problem is a term for that. Okay. So in this case, our PDE is du dx equals 1. And then we have just a general initial condition, in this case, just some g of y. Okay. So notice in our xy plane, the initial curve, so it's just the y-axis. So your initial values are specified here, and then whatever characteristics we come up with, those are the curves along which the solution of a PDE, the values of g of y are going to propagate. Okay. So the first thing you do is you need to fit your given PDE to the general form of a first order PDE, which is AUX plus BUY is equal to C. And I want to emphasize A, B, and C are all allowed to be functions of x, y, and u. Now, if they only depend on x and y, that is a linear PDE. If they also depend on u, then it's a quasi-linear PDE. Okay. Although, for instance, I could have c equal to c, like a function of x, y times u. That's also a linear PDE. Okay. So, in this case, a equals 1, b equals 0, and c equals 1. All right. So, now that you have your values of a, b, and c, the first thing you do for method of characteristics is you define your characteristic equations. And the notes are referred to these as IVPs because these are also initial value problems. You're going to have an ODE plus initial condition for x, y, and u. So you're going to have 3 of them. The idea is solving these ODEs will be simpler than trying to solve the PDE directly. Okay, so your first ODE is dx d tau is equal to a of tau and s. So tau and s are your characteristic variables. And then we have dy d tau is equal to b, and then du d tau is equal to c. All right, so that's why we need to get a, b, and c, so we have our right-hand sides of for our ODE. So 1, 0, and 1 in this case. Then you get the initial conditions of these characteristic equations from the initial condition from your PDE. So when tau is equal to 0, well, for an initial condition, x is always 0. So that's what we put here. And then for y, s basically acts as a parameter for your initial curve. So we could say y of 0s is just equal to s. So for these simple initial conditions, generally s is going to play the role of either x or y. But we're going to see more complicated initial conditions later where it could play the role of one variable or the other. So whichever is convenient, like whichever is not constant, for instance. Okay. And then the right side of the initial condition is used to give you the initial condition for u. So u of 0s is equal to g of s. Okay. All right, so those are the characteristic IVP. So, A, B, and C give you right-hand sides for your ODEs. Your initial conditions for your IVPs come from initial condition for PDE. You're just picking it apart. See, how does x behave, how does y behave, and how does u behave? So all of these come from behavior of x, y, and u on whatever your initial curve is. Okay. All right. So questions about where the characteristic equations come from before we go about actually solving them. Okay. Okay. And fortunately, these particular ones are pretty easy to solve. Okay, so dx d tau is equal to 1, so that means that x of tau s is equal to tau plus the initial value, which is 0, so x is just equal to tau. So in this case, generally, when possible, you'd just be integrating. Some equations will be more difficult to solve than that, but not in this case. Okay, what about y of tau s? Can you just go ahead and integrate that? Yeah, it's going to turn out to be s, because you integrate 0 and you get nothing, you just add on the initial value, which is s. Okay, and what about u? Is it possible to solve that by integrating?
Would not just be tau plus g of x.
Yeah, it works out the same as the equation for x, because the time derivatives are the same, they're just 1. You just have a different initial value, g of s. Okay. Now, some terminology here. All three of these together, these equations define what's referred to in the textbook as the characteristic curves. So each s value describes a different characteristic curve. Each individual curve has tau as a parameter.
Each s values define a different curve.
Sorry, what? Each?
S values define.
Yes. So for navigating along a curve, you use tau, and parameter s is how you go from one curve to another. So you can think of it as a parameter between curves. So if you vary both parameters tau and s, you have a characteristic surface, and that is your solution surface. Okay. So in a sense, we have a solution, except it's not in the form we want. So we need to get the solution, instead of function u of s and tau, or u of tau and s, we want form u of xy. So what you need is to invert a transformation, because right now we have tau and s in terms of x and y. So what you really want is x and y giving you formulas for tau and s. So you just need to be able to go the other way. Okay. All right. So right now we have x is equal to tau, y is equal to s. So in this case, the inversion, I have to admit, it's pretty trivial. Tau is equal to x, s is equal to y. So certainly wasn't interesting, but don't worry, other examples will be. So now we can write down the solution. So u of xy is equal to tau, which is x, plus g of s, but that's g of y. Okay, so that's your solution, your unique solution in this case. All right. Now, actually, I accidentally skipped over something. So these three equations together define the characteristic curves. These two equations together, for x and y as functions of tau and s, these define what are called characteristics. Okay. Those are also very important because they help you understand the behavior of a solution. So like for instance, if you plot the characteristics in the xy plane, then you can see how the initial values of u are propagating through that plane. So in fact, what you can say is, if you take the characteristic curves and you project them into the xy plane, you get the characteristics. Okay. So these merit having a separate term, separate terminology, just because of their importance. So what's happening is, if I look at free space, so x, y, and u. So, for instance, if somewhere up here is a characteristic curve, x of tau s naught. So I'm focusing on a specific value of s to focus, so that we have just one characteristic curve. And then we project that curve down to the xy plane. So this is a characteristic x of tau s naught, y of tau s naught. And then we would look at this same characteristic in the xy plane. In this case, it would look something like that. Okay, so this curve is exactly the same. We're just looking at it from a different point of view. Okay. So what's happening is, if we look at the curves in this case, what is happening as tau changes? Well, tau only influences x. So the idea is, if s is how you choose a characteristic, and tau indicates how you propagate along it, what you do is you can choose y is equal to some constant s naught, and then x is equal to tau. So what's happening is, the characteristics in this initial value problem, okay, because recall, the y-axis is your initial curve. So as tau increases, so these are your characteristics, all the horizontal lines that start at the y-axis, and they just continue to the right as tau increases. Or if you want to allow tau to decrease, then they would go to the left. Okay. But often the tau variable is equated with time. So, okay. Okay, so any questions about characteristics in this case?
Why did it go in the right direction? Because tau is increasing?
Yeah, because x equals tau. Yeah. So if x had been minus tau, then yeah, you'd be going to the left.
It will generally be increasing because it's time.
Yeah. Hold on a second. My screen. Okay. All right. So we're recording again. All right. So now what I'm going to do is I'm going to revisit this. So don't worry, nothing was lost. I'm going to revisit this PDE, but what I'm going to do is just show what could go wrong. I'm going to change the initial condition. So now instead of u of 0y equals g of y, let's change it to u of x0 is h of x. Okay, so now what happens is all of your characteristic IVPs, the ODEs are going to be exactly the same. But now we have u of x of 0s is equal to s, y is equal to 0, and u is equal to h of s. Okay, so now that we've
But
got...
it will be S0, right?
What?
Like, and then u of x of s0, y of s.
Well, we'll just keep the same order between tau and s here. I always use tau first.
Oh, okay.
Yeah.
Okay.
Yeah.
Right.
Okay. Now, as far as solving the characteristic IVPs. So that works out essentially the same. So now we have tau plus s for x, and then y just turns out to be 0. So all characteristic curves are focused on the x-axis, and then u is exactly the same. So we want to, so we have x equal tau plus s, and y equals 0. But what happens when you try to invert? You want to solve for tau and s uniquely in terms of x and y. What goes wrong?
Tau equals x minus s.
Well, yeah, here's the problem. You can't invert because
Y equals 0.
if we inspect the, sorry, I'm going to keep coming over here and making sure that this doesn't go black on me. The transversality condition. So the Jacobian of dx d tau d y ds minus d y d tau dx ds, and all of these are evaluated on the initial curve, so we're restricting to that, must be non-zero. Well, dx d tau is just the coefficient a, and then we have derivative of y naught with respect to s, so the initial condition, and dy d tau is equal to b. So what happens in this case? Well, b is 0. So a is 1, this is 0, b is 0, and x, so x naught is equal to s in this case, so its derivative with respect to s is 1. But the point is, Jacobian is 0 everywhere. So when you have a Jacobian with change of variables being 0, it cannot be inverted. So we have no way to go back. So what's happening geometrically with the solution? So if the Jacobian is 0, that means that the initial curve is tangent to a characteristic. And when it happens, so there's something we cannot have. There has to be some linear independence between the initial curve and all characteristics to have a unique solution. Basically for a problem to be well posed. Basically giving you an ill-posed problem that we cannot find u of xt.
x2 minus x1 is 0.
What?
Like, the gradient will be like, it'll be straight lines going up.
Yeah.
So then
Yeah,
you can't
exactly.
have that. Because-
Yeah, so in fact what's happening is the initial curve is a characteristic. It's worse than being tangent. This is what could happen at a single point, and that's bad enough. But if they actually lay on top of each other, then yeah, that's really bad. So, so we have to be careful about, you can have a perfectly solvable IVP, you change the initial condition and it becomes unsolvable. So that's the cautionary tale with this problem. Okay. So any questions about that situation?
So if you draw the diagram, like how would it sort of look like? I mean,
So what happens is your characteristics are vertical lines now.
right. And the gradient will be, not defined.
Well, actually, characteristics makes no sense at all. Yeah, because S is where it starts, but then actually, oh, you know what? Actually, all your characteristics are contained within the x-axis, and your initial curve is the x-axis. So everything is confined to the x-axis. So you're out of luck. Because the idea is to propagate through the xy plane. Here you're not propagating anywhere beyond the x-axis. Okay, so yeah, sorry about my earlier comment. Yeah, you brought vertical lines. I should have said no. That's not what's going on here. Okay, because for the PDE, we're going to have the horizontal component to the characteristics no matter what because of this tau here. But in the first case, y was s, but now y is 0. So that's why we don't really have a family of characteristic curves, which is what we need here. Okay. So now for our next example. Okay. This one's a lot shorter. Okay, so we have ux plus uy plus u is equal to 1. And our initial condition is more elaborate. So now the initial curve is a parabola. And along this initial curve, the solution is equal to sine x, so it just takes the x value. So we get some rather odd behavior here. Okay, so this leads to the characteristic equations. X, so dx d tau is equal to 1, the coefficient of du dx. dy d tau is equal to 1, the coefficient of du dy. And then du d tau is equal to the u that's on the left side, so that stays on the left side. And then we have a 1 on the right side, so that goes on the right side. Okay. Now we need the initial condition to get our initial conditions for these equations. So x of 0s is equal to s. Y of 0s, we go to the y value now. That's going to be s plus s squared. And then u of 0s is equal to sine x, but that is sine s. Okay. So now our characteristic equations are defined. And now we can, this is a linear PDE. So we can solve these first two separately. So what is x going to be?
Tau plus s.
Yeah, tau plus s. Okay. What is y going to be?
Tau plus s plus s squared.
Yeah, tau plus s squared. Okay. Now for this equation is a little more involved to solve because you have to use an integrating factor. This is a linear first order PDE. So you actually have to use the integrating factor e to the tau. Okay. So you multiply through by the integrating factor e to the tau. Then we have e to the tau u tau is equal to e to the tau. So now we integrate. Both sides. Okay. So we have u is equal to. Okay. So e to the tau u with limits 0 and is equal to the integral from 0 to tau of e to the t. So I'm just using t as a variable of integration. So now when I plug in the limits, I get e to the tau u of S tau minus plug in 0, so I get 1 here. I'm going to get the initial value, which is sine S.
Wait a minute. Why do you have? Why did you like start throwing in T's and taus?
Oh,
Like, why
because-
don't you go ahead and change some part of the way through?
I had to change something because I'm going to use 0 and tau as my limits of integration.
Okay.
I need a different letter for my integration variable. Okay. Okay. So that's the left side. On the right side, I just integrate this from 0 to tau. Well, that is e to the tau minus 1. Okay. So now I can rearrange this to solve for u. So that's going to be, okay, 1 plus sine s minus 1 times e to the minus tau. Okay. So now I have my characteristic curves in s tau terms. But like before, I need to invert and get back to x and t. So how can we do that? Well, notice if we take y minus x, we get cancellation here, and all that's left is an s squared. So we can say y minus x square root is equal to s. All right. And then what we can do is, now that we have s, we can substitute that back in here to get tau. So tau is equal to x minus s. Okay. So inversion was just fine. So now I can substitute these expressions for s and tau back into here and get my solution u of x t. So that's going to be 1 plus sine square root of y minus x minus 1 times e to the minus tau, which is x minus the square root of y minus x. Okay, so this is my final answer.
So you want u x t or x y?
Sorry, xy. Yes, it still bugs me how the book does xy for these first order problems when in applications they almost always depend on x and t, but whatever. Okay, so in this case we had no problem inverting. At least algebraically see how to do it. If you were to check a transversality condition, you would find that it's non-zero. Everywhere except when s is equal to 0. But I actually forgot one condition in the problem. We're only assuming x is positive.
Is that?
What?
Is that like 1 plus sine of all that crap x, comma e to the? I'm just checking.
Okay, all of this
That.
times the x. So only this is multiplied by the exponential.
So is it square root over the negative one? Is over the?
No, it's
square-
only.
I'm getting you. Okay.
Yeah, so only y minus x has a square root because of the inversion.
And that's times the e to the.
Yeah.
Okay. All right. I just get
I think I have enough room so I can
I was
write it
getting
better.
so confused. Trying to copy it. Okay.
Square root x times.
Gotcha. Okay.
Okay.
Thank you. Sorry.
Okay. Any other questions about this one? Okay. All right. Now, the next example.
the curves for these will like go along the XY plane.
Oh,
And
well, let's see. So what happens is, okay. So for each S, you start an initial curve, and so, okay, so I'll go back to the picture here. So here's a point on the initial curve. And what happens is, so it's of a form S for the x coordinate, S plus S squared for y coordinate. But what happens to both x and y as tau increases? You're just adding tau. So it's going to go off this way with slope 1. So start number 1 here. So this is what all of your characteristics look like.
okay.
Yeah. And that's just because to see how a characteristic curve behaves, once you go to the initial point, just see what happens to tau. And what we're doing, we're just adding tau to both. Okay. Okay. All right. Now, all right, so the next one, we have minus y du dx plus x du dy is equal to u. And then our initial condition is to have a plain old x-axis for initial curve. And it's just some given function psi of x. Okay, so your characteristic equations okay. So what we have here is so dx d tau is a coefficient of du dx if it's minus y. Dy d tau is a coefficient of du dy, so that's going to be x. And initial condition, x of 0 tau is what's happening to x in the initial condition. Well, that's the parameter s. Y of 0 tau is 0. And then we have du d tau is equal to just u. It's the right-hand side. And then the initial condition for that one is just psi of s. Okay. Now, this problem presents a complication that the previous examples didn't. And that is, the equations for x and y are coupled together. Now, those of you who just sat in my 561 class, numerical analysis, actually should recognize this system.
Right.
It's from your first homework. So x prime is equal to minus y, y prime is equal to x, and also initial conditions. X of 0 is equal to s, y of 0 is equal to 0. If you differentiate this equation, you get x double prime is equal to minus y prime, but that's yeah, so that's yeah, so it's actually going to be equal to minus x. So if x double prime equals minus x, what function satisfies that? Sine and cosine. So your general solution is sine and cosine, but because of the initial conditions, what you actually get is x of tau s is equal to s cosine tau, and y of tau s is equal to s sine tau. Now, in general, it would be an arbitrary linear combination of sines and cosines, but the initial condition narrows it down to this simple form. So in other words, your characteristics are circles. And the center is at the origin, and the radius is s. All right. So we have this kind of situation where your solution is propagating along these curves. So at certain values, S1, S2, S3, as tau increases, you're going around these circles. Okay. But your initial curve is the x-axis. So your values of u start here on this initial curve, and they propagate in a circular direction. Okay, so what about this last equation? Du d tau is equal to u. What's the solution to that?
U tau.
No, because these are the same variables, so you can't just integrate both sides.
Right. So you have to take it to the other side. Du d tau minus u.
That's overkill. Well,
Just be e to the tau.
yes, e to the tau.
Times e to the tau.
Yeah, e to the tau times the initial value, which is psi of s.
Yeah, u prime equals u. Yes.
Yeah. Okay, so now we have our solution in characteristic variables, but we need a solution u of x, y. So we need to invert. So if we have this relationship, x and y expressed in terms of s and tau, what kind of coordinates are s and tau? Normally expressed using different letters in this.
Polar.
They're polar coordinates. Who can tell me how to convert? Okay, well, polar coordinates are customarily r and theta. So which is r and which is theta?
Yes, it are.
S is r and tau is theta. So does anyone remember how to convert? And so if you're given x and y, how do you convert to r and theta, or in this case s and tau? So what would go here?
Square root of x squared. Square.
Yeah, and what about the other one? Yeah, now we're going to go with, inverse tangent of what?
Y over x.
Y over x, assuming that's the angle of x is positive. So actually, by choosing this, we're restricting ourselves to the right half plane. So now we can write this as e to the tau times psi of s. Okay. Again, I guess the transformation from polar to Cartesian is well known to be invertible, except where? Where is it not invertible?
The origin?
Yeah, just the origin. In which case you definitely have a problem here. Because that could be anything. Okay. Now the thing is, normally the characteristics and the initial curve should only intersect once. Here they clearly intersect twice, but because we made this choice for inverting, for the inversion, we assume x is positive. This is the only intersection on the positive x-axis that actually counts. Okay. So this solution is well defined. So for instance, what we could do is, if we corrected this, say, inverse tangent of y over x plus pi, that would put us in the space for a negative x. All right, so any questions about that one? So you have 25 minutes, hopefully get together 2 examples before many of you go on to suffer an analysis. so this is a strange one. Du dx plus 3y to the 2/3 uy is equal to 2. And then our initial condition is u of x1. So this our initial curve is not the x-axis, but 1 unit up from that. And then this value is 1 plus x. Okay. So our characteristic equations. So dx d tau is the coefficient of du dx, which is 1. X of 0 tau is just equal to 0s. This is equal to s, because our initial curve is a horizontal line. dy d tau is equal to 3y to the 2/3, the coefficient of du dy. And then y of 0s is equal to 1. And then finally, du d tau is equal to 2, just the right-hand side. And u of 0s is equal to 1 plus s. Okay. Now, well, two of these equations are easy to solve, thankfully.
Why did we switch from tau to s?
I'm sorry, what?
Why did we switch, like, then we were doing x of 0 tau, and now you're doing x of 0 s? Like, why did we do that?
Oh, because I messed up over here.
That's what we were doing the whole time. Oh, no, it's not. Okay, I see.
Yeah, we were doing 0s the whole time.
Yeah, tau is not supposed to be in the initial conditions. Yeah, because I almost did it again there, and it's like, that doesn't sound right. I'm going to stop myself. Okay, so, alright, so video watchers in your notes for just the last example, it's 0s, not 0 tau. Okay. Sorry about that. This is why I type my notes. Except I don't always read them, obviously. Okay. Okay. All right. So what is x?
Tau plus s.
Tau plus x. Okay. Y is going to be a little harder to solve. We'll come back to that in a moment. What about u? This is a relatively easy equation to solve.
Well, 2 tau plus 2 tau plus 1 plus s.
Yeah. Okay. All right. So what about y? This is it's a nonlinear equation, but it's separable. So I have dy over 3y to the 2/3 is equal to d tau. So what I'm going to do is I integrate both sides. So I have 1/3 y to the minus 2/3. So I use the power rule, and I get y to the 1/3 over 1/3 is equal to tau plus c. Now the 3 and the 1/3, thankfully, cancel out. So now I'm going to substitute tau equals 0 and make sure I get 1. So if I plug in tau equals 0 and y has to be 1, what should my c be? Yeah. So y equals 1, tau equals 0, therefore c equals 1. So now I have y to the 1/3 is equal to tau plus 1. So now I can just take the cube root of both sides. So y is equal to,
So you cube both sides.
yes, cube both sides. This day needs to be over. It's tau plus 1 cubed. So now we have all of our characteristic equations solved. Okay, but now, like before, we need to invert. But now we just handle that algebraically, because we can take this equation and solve it easily enough for tau. In fact, it's easier to go back to this. So tau is equal to
y to the 1/3.
you know, y to 1/3 minus 1. And then we could plug that back into our equation for x. So s is equal to x minus tau. Okay, so so that's no problem. So now we can take these and substitute them in here to get our solution u as a function of x and y. So that's going to be 2 tau plus 1 plus s. Okay. But as you can see, there's going to be a lot of cancellation. In fact, all of the constants are going to cancel, and this simplifies to just x plus y to the 1/3. Okay. All right. Okay. Now, one thing I should point out, though, is if you go back to the equation for y, we went ahead and solved it, but there's another solution. Y equals 0. So we actually have like an extra characteristic. But fortunately, our solution is still well defined, at least near the initial curve, because the initial curve is not y equals 0, it's not the x-axis, it's y equals 1. But what would happen is you'd have a situation where whatever characteristic curves we get will cross this one. So you're actually going to have bad behavior around y equals 0. And in fact, if we look at this solution here, it is not differentiable. At y equals 0. And at least our initial curve steered clear of that problem, but it's something to be aware of. And some of our homework problems get into, okay, you go ahead and solve a problem using method of characteristics, but when you look back at what you get, you see, well, where is it defined? And do you actually have a unique solution? Because in all of these, if you go ahead and check the transversality condition, for most of the examples that we have, except that one early on, it checks out that it's non-zero. Okay. All right. So any questions about this one before my last example of the day? Okay.
What significance does this have, like y equals 0 being the solution have?
Oh, because what happens is all the characteristic curves that we compute here,
Right.
these would, if you let tau vary, eventually, if you let tau go negative, for instance, so y would eventually become 0. So these characteristics will cross that characteristic. When characteristics cross, you have a shock. And we're going to talk about shocks more later in the chapter when we deal with nonlinear equations. So the thing is, normally with linear equations, you don't have characteristics cross. But in this case, you do. So that's a recipe for non-uniqueness of the solution. Okay. Yeah, so it's like having an extra characteristic that you don't want. Okay. All right. So finally we have, this is a quasi-linear PDE. So we have y plus u du dx plus y du dy equals x minus y. So because the coefficient of du dx depends on u, that is what makes it no longer a linear PDE. Okay. It's almost linear in a way because it still has coefficient ux plus coefficient uy is coefficient. But when the coefficients can depend on u, these coefficients, then that's no longer linear. Okay, and then our initial condition. Oh, interesting. It's the same initial condition as last time. Just a coincidence, though. Okay, so now if we look at the characteristic initial value problems, we have the x d tau is equal to y plus u, the coefficient du dx. dy d tau is equal to y, this coefficient. And then du d tau is equal to right hand side, so that's x minus y. And then initial values, x of 0s is equal to s, y of 0s is equal to 1, u of 0s is equal to 1 plus s. Okay, now, once again, we have two of the equations being coupled. When you have a linear PDE, these equations are always uncoupled from this one, but this is not a linear PDE, so now these two are coupled. So we're going to have to use a little more ingenuity to solve these two equations. What about the equation for y? What's the solution of that? That one's the easy one.
Tau?
No.
Not just
E to the tau
E to the tau,
plus,
because dy dt is equal to itself.
well, times 1, which is 1.
Times the initial value, yeah. Okay, so this one's no problem. So y is equal to e to the tau. Now, these two are kind of a pain, but if you use a little trickery, these actually become a lot easier to solve. And this is a good trick to have in your repertoire. So what I'm going to do is I'm going to take linear, because at least this system, even though the original PDE is not linear, this system is a linear system. We take x and u together. So I can take linear combinations of these equations to get new equations that will be easier to solve. So I'm going to take these linear combinations. I'm going to let w equal x plus u, and I'm going to let v equal x minus u. Okay. So what happens is dw d tau is equal to the derivative for x plus the derivative for y. And what happens? What simplifies?
Y cancel.
The y's cancel, you're left with u plus x, so that's just w. So you have a nice simple equation there. And then the initial values, you'll just add them. So w of 0s is just the sum of these two, so that's 1 plus 2s. So what's w going to be?
Again, e to the, okay. Equal
Yes, it's
e to the tau
yeah.
times 1 plus 2s.
Yeah, times the initial value. So it's 1 plus 2s e to the tau. Okay. All right. Now what about v? Well, dv d tau is equal to, okay, so we have x minus u. So y plus u minus x minus y. Okay, so what happens in this case, you don't get cancellation, but what you do get is, okay, 2y plus u minus x, but that's the same as minus v. So you get v prime is equal to 2y minus v. Now, y is known, so we can fill that in. So 2e to the tau minus v. And then the initial values, we'll subtract them. So v of 0s is equal to this minus this, so we just get minus 1. Okay. So now we just have to solve that. Okay, so dv d tau, I'm going to rearrange it, plus v is equal to 2e to the tau. This is a linear equation that needs an integrating factor. The integrating factor is e to the tau. So what you get is e to the tau v prime is equal to 2e to the 2 tau. So, because I'm multiplying both sides. So now I integrate both sides of this, and you get e to the tau v minus the initial value, which is minus 1, is equal to e to the 2 tau e to the 2 tau minus 1. Okay. So, oh, wait. I need, oh. Okay, the integral of this is e to the 2 tau. Okay. Oh,
Because you get a 1/2, right?
yeah. I need my initial condition. Okay. Okay.
So you get e to the tv all prime equals 2 to the 2 tau. And you get e to the tau v, and then you do minus 1.
Yeah. Okay. Okay, because I'm basically like integrating from 0 to tau in a way. So I've
But you're integrating from -1 tau, right?
so when I plug in tau equals 0, I get v equal minus 1. That's where that comes from.
So
Yeah.
this is integrating from
Yeah. Yeah.
0 to
Okay. And then when I integrate this, I just get e to the 2 tau.
yeah, because you get a 1/2, right?
Yeah. Yes. Okay. So v is going to be e to the minus tau, e to the 2 tau minus 1, minus 1. Okay. Okay, yeah. So what I get is e to the tau minus 2, because these combine, e to the minus tau. Okay, so that's my v. Okay. It satisfies the initial condition also. Okay. Questions about that? Because basically what I'm doing is I'm taking this and I'm doing a definite integral. And really I should change the letter in here, but you get the idea. Okay. Okay, because here we have initial values on both sides at tau equals 0. Okay, so now I have w and v, but what I really need are x and u. So I need to invert that. Fortunately, that's not hard to do. Okay, so w is 1 plus 2s. Oh, need to move this. Okay, I got 5 minutes. Barely doable. E to the tau, but that's equal to x plus u. V equals e to the tau minus 2e to the minus tau. That's equal to x minus u. So when you invert this system of equations, you get, like if you add these two together, you get w plus v is equal to 2x. So x is equal to w plus v over 2, and u is equal to w minus v over 2. So it's just from row operations on this system. So then you can combine these in the appropriate way. So x turns out to be 1 plus s e to the tau minus e to the minus tau. And then u is s e to the tau plus e to the minus tau. Okay, so by solving a simple equation of w and v, it's a linear combinations of x and u. So we just undo linear combinations. Because what's happening is, this is from the fact that, look at this matrix, 1, 1, 1, minus 1. The inverse is 1/2, 1, 1, 1, minus 1. Okay. Yeah. Okay. Now, yeah. So now the last thing to do is, I want to check the transversality condition. So the Jacobian is a times the derivative of y naught with respect to s minus b derivative of x naught with respect to s. Well, a, that coefficient is on the initial curve is equal to 1 plus 1 plus s, because a is equal to y plus u. So these are the values on the initial curve. Y is equal to, y is equal to, where's my initial condition? Oh, y is equal to 1 on the initial curve, so its derivative is 0. So that's this part right here. B is equal to y on the initial curve, that's 1. And then x is equal to s on the initial curve, so that's 1. So that means that the Jacobian is equal to minus 1. So because the Jacobian is non-zero, that means we can invert. So the thing is, so for inverting purposes, what do we have? We have x is equal to this, u is equal to this, and y is equal to just e to the tau. So we can take e to the tau and plug that in here. So that means that x is equal to 1 plus s y minus 1 over y. And u is equal to sy plus 1 over y. So at least we can get tau completely out of the picture. And now what we can do is, if I go ahead and rewrite this, I have sy is equal to x minus y plus 1 over y. So all I do is I just isolated sy. And I could take that and substitute that in here. So now that gives me my solution, u of xy is equal to x minus y plus 1 over y plus 1 over y again. So it gives me 2 over y. And that is my final solution. Note the solution is not defined in the, when y equals 0 on the x-axis, but that wasn't our initial curve. Our initial curve is a line y equals 1, so we don't have a problem here. Okay. Well, that was exhausting. Questions about this last example? So the procedure, the general procedure is always the same. Form your characteristic IVPs with your initial conditions from the PD's initial condition. Solve equations by whatever crazy things you have to do to solve them, or sometimes they're not as crazy. And then invert to get the solution U in terms of your original independent variables. Assuming a transversality condition is satisfied, which if you have a bad initial condition, it might not be.
So should we always check before we convert?
Well, not necessarily. Sometimes it's obvious to see how to invert, and just go for it algebraically.
Right.
But if you seem to be having trouble, then it's worth checking this, because maybe you're trying to solve an impossible problem. Okay, so good luck with that homework. I'll take homework 1 if you got it. Okay.